started. We're going to be doing recrystallization. So one of the things that's going to become more and more important for each of these is being able to recognize your intermolecular forces. Okay? So go through, understand this chart, understand what it means and how it's functioning. Okay? So we used it to interpret melting points. When we look at water versus methane, water has what types of bonds? Polar covalent bonds. Okay? Which means what type of force? Okay, there's two answers possible for that, though I'm going to be obnoxious and say the one I was looking for, the dipole-dipole. Once we have a dipole-dipole force, we can then try and evaluate that further. Okay? Do we have the circumstances for hydrogen bonding to be true? Do we have a hydrogen bound to oxygen, nitrogen, or fluorine? Yes, that means water has hydrogen bonding. Okay? When we looked at methane, what intermolecular force does methane have? Or bonds does methane have? Let's try that. Sounded like a covalent. Wasn't quite sure. Okay? It's got covalent bonds, which means what types of forces? We're looking at London dispersion. If we have London dispersion forces, we can now compare the intermolecular forces between those two compounds. Which one has the stronger force? Water, which means it has a higher melting point or a higher boiling point. What happens in that second case? Ethane versus methane. What types of bonds do we have in each of those? Good answer. They're all covalent. Okay, that was kind of funny, I thought. If we've got covalent bonds, what kind of forces do we have?
London dispersion.
We've got London dispersion forces. So we've got the same force in both of these. So we might initially predict that we can't determine which one has a higher melting point. So we have to take it one step further and look at the amount of the force. Okay? In the case of ethane, it's a larger structure, which means there's more opportunities to build those weak London dispersion forces. So we now have more forces, higher energy to break it apart, okay, or break it away from other molecules. The other physical properties that we're going to see this semester are solubility, ultimately reactivity. We're going to look at solubility today. As far as the techniques, we already looked at melting point. We won't have to worry about boiling point, thankfully. We're going to do crystallization this week. I believe next week is extraction. We'll also do TLC in several weeks after that. All of them go back to these understanding these same intermolecular forces and the bonds that they come from. Okay? So you need to be able to interpret this. When it comes to solubility, okay, we can use a variety of predicting techniques, just like we could do with melting point. Okay? So the first thing we'll look for is similar or the strongest amount intermolecular force. So the common rule that comes out of solubility is like dissolves like. Okay? That's like forces interact with like forces. So what we'll look for is look for the similar strongest force in between them. If they have similar strongest forces, more than likely those two compounds will mix because the polarity or the partial charges generated from those strong forces can neutralize across molecules. Okay? So that's a good first approximation. After that, if we predict incorrectly, we'll have to look for other things. We can look for the total intermolecular forces. So maybe a molecule is composed of something more than just hydrogen bonding. You know, you look at water and all you really get are hydrogen bonding as your strongest force. But there are other forces that contribute to an overall structure. Okay, so we need to evaluate those in total as well when we're looking at solubility. The very last thing that very rarely shows up, and it shows up in the group activity, but you probably won't see it again after that, is looking for structural considerations. Okay? Does the structure prevent or allow certain types of interactions where in another circumstance with those same types of forces, does it change? Okay? So let's go through and apply some of these. If we were going to look at those first two structures, we've got benzene and we have water. What types of intermolecular forces does water have? What's our strongest force? Okay, let's take it a step further back. What bonds do we have in water? Polar covalent. What types of bonds or what types of forces would a polar covalent bond generate? Hydrogen bonding. So we're looking at a hydrogen bonding interaction. What happens when we move to benzene? Okay, when we look at benzene, we've got carbons to carbons and carbons to hydrogens. What types of bonds are those? We're looking at covalent. If we have covalent bonds, what types of forces? We get London dispersion, or LDF to keep it short. If we now compare those two forces, are they similar? No. Hydrogen bonding is a very polar interaction. We have very large partial charges. London dispersion generates no partial charge. If we've got dissimilar forces, they do not want to interact with each other. What does that mean about their solubility? Insoluble. Okay? What happens if we move to the next compound? Say methanol. What types of bonds are in methanol? Okay. We've got some covalent bonding, and we have some polar covalent bonding. What does that mean about intermolecular forces? What intermolecular force would we predict from our polar covalent bond? Dipole-dipole, taken a step further. Hydrogen bonding. Why do we have hydrogen bonding? We have a hydrogen bound to oxygen, nitrogen, or fluorine. What does our covalent section have as far as intermolecular forces? London dispersion forces. So now we can try and compare this structure back to water. Would we expect water and methanol to be soluble or mix? They both have very similar strong forces, hydrogen bonding. The amount of London dispersion force that methanol brings in is relatively small. So we could predict the hydrogen bonding interaction would overwhelm our London dispersion force, and we would expect those two to mix. How do we find out if they actually mix? Good answer. Let's mix them. So we go into the lab, we mix them together and see if they mix. Indeed, they do. Okay? What happens if we try and mix methanol with benzene? They both have London dispersion forces. What we have to do is evaluate the interactions between those. Methanol has two possibilities associated with it, the London dispersion and the hydrogen bonding. Hydrogen bonding was strong enough to overwhelm the London dispersion effect when we looked at water. So what do you think is going to be the primary force when we look at comparing it to benzene? Probably still hydrogen bonding, which would say what about the solubility of those two? Insoluble or not soluble? Okay, how about this last structure that we're looking at, which I'm not going to count it all, but I think it's decanol. What types of bonding do we have out there that I just highlighted? We've got covalent bonding, which means what force? London dispersion forces. What kind of intermolecular force do we have within the OH? Polar covalent bonds, hydrogen bonding for our force. So now we try and take this back and compare it. Would we expect decanol to be soluble with water? Should they mix? They both have that hydrogen bonding interaction. So as our first approximation, we'd say yes, they do. We go into the lab, what do we find out? They don't mix. Okay? So now we've come up with a theory. We said they would mix. They didn't mix, so what do we have to do? We adjust our theory. So what's different about dodecanol or decanol? Why did it not dissolve where methanol did? What about the structure? It's that long covalent tail generating those London dispersion forces. We've added enough weaker forces to dominate the overall intermolecular forces for that compound. Okay? And what we end up comparing when we look at decanol and water is water with hydrogen bonding and our decanol with primarily London dispersion forces. Would we expect those two to be soluble? No. Okay? Where's that line? Okay, where you've added enough carbons that it's no longer going to be soluble in water. We would hope there's a line, right? Lines are nice. Unfortunately, we don't really get a line when it comes to solubility. A lot of it is guess and check. We kind of just predict, see what happens, and then have to go back to the results and come up with a theory to explain that. Okay? So when you're asked on a test what's going to be happening in certain cases, they will be very clear delineations. Say water and benzene. Okay? What is the rough approximate line? 4 carbons typically outweigh hydrogen bonding, a single hydrogen bonding interaction. Okay? Most organic compounds have a lot of carbons in them. Most of them are water insoluble. Okay? Just as a general rough rule. Okay? Questions about that? So now what we're going to try and do is apply solubility, see what we can do with it. We're going to use it as far as we're concerned with separation, but if we want to sound a little fancier, we can call it purification. Okay? The technique that we're going to look at this week is going to be recrystallization, okay? Which is primarily a purification technique. It's not quite as nicely described as separation. Okay? So if we're going to go through and purify something, we're going to have to start with something that's impure. How would we know it was impure to begin with? We could look at our melting points. What would we see in the melting point? We'd have a nice broad range. If we knew what our compound was, it would be lower than our literature value typically. So we've got a way that we can look for impurities. Okay? And we're going to try and come up with some way to separate these things. So ultimately, if we looked at this as a picture diagram, what would our pure sample look like? Let's see if I got this set up right. Yep. We'd get them completely separated away from each other. Okay, well, how do we do that? How do we move from our impure to the pure, where we've got them separated? What do we have to do? Okay, you don't have to think about this chemically. Think about it as just shapes. On the playground, you're trying to get those away from each other. What do you have to do? You're physically separate. Break them away from each other. Okay? I'm going to have to break out that block and probably that block and get them out of the way so that I can then pull the circle out. Once that's done, I can shift those blocks, reorganize, and put them all back together. Okay? So the very first thing with all separation or purification schemes is that I have to somehow break all interactions between those blocks so that I can put them back in the correct order that I want them in. Okay? So that's the trick with this. How do we get those all broken away from each other? Okay, if we looked at the playground, all we had to do is physically pick them up and move them. Okay, there are purification schemes where someone took a microscope, looked down at a crystal structure, and individually hand-moved each individual crystal away from other impurities. It's a bit tedious. Okay, I've never done it, thankfully. So what else could we do to break all of those forces? Okay, filtering would work in only certain circumstances. Filtering is not going to break the intermolecular forces, though. I have to break every single one of those interactions that's holding it together as a solid. If it's a solid, I can't filter. You don't filter solids away from solids. Okay, we could try and heat it up. What happens when we heat up a solid? We start to break the intermolecular forces, and it becomes a liquid. Okay? Is it going to be particularly easy to separate a liquid away from a liquid? Yeah, that's kind of questionable. Maybe we could add more heat. What happens if we add more heat? We move it into the gas phase. Now all of the intermolecular forces are 100% broken. That's exactly what we were targeting here. Okay, so that's a good idea, except how hot do you think we're going to have to get all of our compounds up into a gas state?
Incredibly high.
Probably really high. Okay, another further complication behind that. We're all made of organic compounds. Okay? we try to melt or even turn ourselves into the gas phase, does that work really well? No. We kind of combust, react, turn into CO2, other things other than ourselves. Okay? We can't really do that with organic molecules. They'll decompose too readily. Okay? So we have to come up with a more mellow way to get them to separate. Okay? So instead of directly heating, what we can do is add a third substance, like a solvent. So we can hope that we add this third substance, and as it comes in there, it starts to interact with one and not the other. So let's say we had a solution of sand, or a solid mixture of sand and salt. Okay, how could I separate the sand away from the salt? I add water. What happens to the salt? Dissolves in the water. And I now have a liquid solution and a solid. How do I separate the liquid from the solid? Now I can filter. Okay? So what we're trying to do is to take advantage of that solubility. I know it sounds ridiculously simple. Okay? That's because in theory it kind of is. Okay? The technique is entirely different. Okay? That only allows us to go based on one particular circumstance. Okay? We'd have to find a solvent that completely dissolves only one of our compounds but not the other. That's a little bit tricky. Taken a little bit further, if I try to add water, let's say I've got sand and salt in these crystals here. The blue will be our sand, the salt will be the orange sphere. How does water, whoops, don't go to the next slide. How does water get in and remove that sphere? The sphere is our salt. So our salt particle is that orange circle. And sand is the blue squares. How does water get that salt molecule out of that structure?
With the water dissolving the salt?
Good call. Water would need to dissolve the salt. Except, where's the salt? Inside the sand.
You might have to make some sort of bonds or something.
We'd have to break the intermolecular forces holding those sand particles together. Okay? So we could try and shake it up. That can help. We could try and grind it.
Stirring.
We could still try and stir. What we're trying to do is maximize the surface area. But if that salt particle is literally locked within a sand sphere, it doesn't matter how much we grind or shake or stir, it's not coming out of there. Okay? So while this method may work in bulk situations where we've got very clearly two separate different things, it doesn't work for us as far as organic chemistry goes. Okay? We need something that's going to break apart and dissolve both species so that we can get everything out and into the open. Okay? And that's what's going to happen with our difficult separation. Okay? What we're going to hope is that our solvent or our third substance is going to interact preferentially with one over the other. Okay? Which is similar to what we had before, but we're going to add in another caveat here. We're going to end up making sure that it's only under particular circumstances. What's the easiest circumstance or physical situation that we could affect or change? We can change the temperature. So what we're going to hope is that as we add temperature or add heat to our reaction, the solvent starts to interact with more or both of them, and as we remove heat from the system, the solvent starts to interact only with one and not with the other. Okay, so the heat will allow us to get everything to dissolve, and then once we cool it down, we can end up getting our crystals back. Okay? So we're going to have to rely on solubility changing with temperature for each of our compounds. Okay? So some things that we can typically observe when it comes to solubility. Most solutes dissolve independent of the presence of other solutes. Okay? So if I take an individual solution or solvent and I want to dissolve stars in, I think those are dots. Okay? At 0 degrees Celsius, I can get 7 molecules to dissolve. Okay? So what we're saying by that is the stars, 5 stars will dissolve, and 2 dots will dissolve at 0 degrees Celsius. They do not affect each other's solubility. Okay? Does that make sense? A head shake can be helpful. Yeah, okay. The other big thing that we'll notice is that solubility typically has a very strong and direct relationship to temperature. Okay? So you might notice that at 0 degrees Celsius, we may be able to get 7 molecules to dissolve, but what happens at 75 degrees Celsius? We can get a lot more molecules to dissolve. Why does that make sense? Does it make sense? What happens to a solid when you heat it up? Gets more excited, starts to move a little bit more until eventually it moves enough that it stops becoming a solid and becomes a liquid, or ultimately into a gas. So if we go back to our previous situation, what's happening if we ignored all of our solvent molecules in this case is that we could have just heated this all up to a gas phase, which is what we were initially trying to do to begin with, but we said the gas phase would decompose our organic compounds. We're using the solvent to allow us to get into that gas phase-like state, which then allows us to separate things. Okay? Heat is facilitating the breaking of the intermolecular forces, which is the exact same thing that our solvent does. Okay, so it's kind of a nice symbiotic relationship. The next big fun part, particularly when it comes to any kind of science, is we want to graphically represent everything that we can get as neatly as possible. Okay? So what we're going to do is look at solubility and how it relates to temperature and start to plot some pieces of information onto this. Okay? Before you start any interpretation of a graph, you should probably identify some really simple, easy things first. Okay? They're usually so simple and easy that most people give me a hard time for even asking the question. Okay? What can you tell me about that orange dot? I'd say it's orange. It's a valid answer. Okay, I'm not on the solubility curve, only on the temperature curve. It's at low temperature, also known as cold. How about this next orange dot? There we go. Like I said, there's some simple questions, but it allows for interpreting the graph properly. Now where do you think we'll move? Onto our solubility curve. How about right here, our red dot? What can you tell me about that? Highly soluble. Okay? For me, I would abbreviate that as just soluble, just because I'm lazy, and highly is too many letters. Okay, what happens when we move down here? Not soluble, but we can get even lazier than that. Save one letter. We're looking at insoluble. Okay? As simple as it may be to put this information on here, it can help us then interpret where our information should slide on this graph. So if we pick something that is always insoluble, where should it be? We should have a straight line at the bottom of our graph. So like this, right? What did that show?
Always cold.
It's always cold. Our temperature doesn't affect solubility. We want to see where our temperature does affect solubility. Or actually, in this case, it's always insoluble. So there's something that's always insoluble. What if something's always soluble?
Raise that line.
We're just going to run it up at the top. Okay? What if it's soluble only at high temperatures? So where's high temperatures? Probably at our hot end. And it has to be soluble. Where's soluble? It's up at our top. So if we want something that's soluble only at high temperatures, what does that mean it's going to be at low temperatures? Insoluble. So we have to somehow connect these two lines. How can we do that? Two dots. I said dots. Okay, there we go. What if something's soluble only at low temperatures? Okay, good first answer. It doesn't make sense, but it can physically happen. How do we get something soluble only at low temperatures? So we go to where it's low, which is probably cold, go to soluble, and we'd be looking at a line going the other direction. Okay? It is incredibly easy to get these lines swapped and misplaced in different circumstances. Okay? So please watch out for that, because you will see an interpretation of this graph on every quiz. Okay? With different aspects of it. So make sure you understand how to apply it and what's going on with this. If we take this back to our recrystallization, what did we say we want to happen to our compound? Okay, we want one compound to dissolve, so it should be soluble. So ideally, our impurity stays soluble the whole time. What would we want for our target compound? We could jump to just straight insoluble, but that comes back to that sand and salt issue. It still needs to be soluble at some point. So what I'm going to do, let's go ahead and just clean all this. If we picked an impurity that ran there, our target compound, we need to be able to separate it in some fashion or another. Okay, it still needs to be able to dissolve. Where was the most likely case where we can get something to dissolve? High temperatures. We also want our compound, our target compound, to have a varying solubility, which means as we cool it down, our solubility goes down. When do I separate my impurity from the target compound? When the temperature is low. How do I know the temperature needs to be low? Compare the lines. If we look at low temperature, the target compound is insoluble. What about your impurity? Still soluble. What if you'd gone to a high temperature? They'd both be soluble. You wouldn't be able to separate them because they're both dissolved. Okay? So it's a question of interpreting each of these cases and trying to align them as best you can. What's the easiest way to separate a solution from our now insoluble target? Filter. Okay? Kind of makes sense? Okay. So as far as being prepared for the experiment, there is a YouTube video that takes you through it. Like I said, I'll fix the link so that you can link directly from Blackboard. Read through the posted procedure during the video, give you an idea of what's going on with it. In general, your procedure is going to be getting the solid, putting it in a conical vial, heating the solid and the solvent, okay, at the same time. Why do we want to keep the solid hot as well? What happens if we take our hot solvent and add it to our solid, but it's not on the hot plate? What happens to the temperature?
I think it does decrease.
It cools down. What happens to the solubility of your compound when it's cold?
It reduces.
It's very, very low. The idea is we have to get everything to dissolve first. We want to make sure everything stays hot. Okay? So we'll add our very hot solvent. It should be boiling to our crystals until it completely dissolves. Once it completely dissolves, what do we need to do? We should cool it down so that we can get our crystals to precipitate back out. Okay? If you're lucky and you watch that carefully, you can actually see the crystals start to form. It is actually kind of neat to see them crystallize. You now got crystals inside a giant solution. What do you need to do? Filter. You can dry by keeping your filtration system running to try and pull more moisture out of it. You can then obtain a melting point. Why would you obtain the melting point? Okay, I'm going to try table C first. Table C. What do you guys think? Why should we obtain a melting point?
Identification.
So we want to identify the compound. Sorry, I had to pick out tables because I couldn't hear everything. Too many answers. We want to be able to identify what compound it is. That's a good idea. How about table S? What's another option? Why else should we take a melting point? Purity. The whole goal of the recrystallization was to purify the compound. We want to be able to go to the end, identify our compound, and verify that we actually did it correct. Okay? Your TA should be able to cover any other issues in the lab. That was absolutely amazing because I'm finished.